In this video, we're going to be discussing comparison, logical, and bitwise operators in Python. Python supports the typical set of comparison operators, including less than or equal, greater than or equal, equals or equality, and not equals. Each of these comparison operators will compare the values of their operands and return true or false depending on the values present and the comparison operation itself. For example, 5 less than 8 returns true since the integer 5 is indeed less than 8. 4 greater or equal to 10 will return false. But notice that since Python, like most languages, uses two characters for this operator, the greater than or right arrow bracket character, immediately followed by the equal sign character. There must not be any space between these two characters. If you attempt to add a space between them, the interpreter will actually raise an exception. That means it's going to give us back an error. Now, of course, if we remove the space and run the block again, we get false as we would expect. Likewise, the equals operator and the not equals operator must not include any spaces. Python also includes operators for boolean and, or, and not. But unlike several popular languages, Python has opted to use the English words for these operators rather than the typical set of symbols. This is actually quite nice because it can help make your code much more readable. So for example, we can write not, and then in parentheses, 5 greater than 8, and 3 greater than or equal to 2. And when we run the block, we get back true. The parentheses here have precedence, so the and expression contained within them is evaluated first. In this expression, the left side would be evaluated first, so 5 is greater than 8, which is false. Now we know from our truth table above that if either input to the and is false, then the result will always be false. And it turns out that Python is also aware of this, and so the Boolean operators and or are called short circuit operators, meaning that when they find a situation like this, where the end result is known even before evaluating all operands, then the interpreter will skip the evaluation of the second operand and immediately return the result. This is great since it saves time, but there are cases where this can get you in trouble, so we actually have a section covering only this topic later on. But to return to our example, the and expression within the parentheses is false, and of course not false is true, so we see that the output here is in fact true. For those that need a reminder on operator precedence, I've given you a link here to the documentation describing all the operators and the order in which they'll be evaluated. There are two other operators that I'd like to quickly introduce, and those are in and is, each of which can be coupled with the operator not that we just saw above. The operator in tests for containment, meaning that if I have an object that contains other objects, for instance, a list of integers, the in operator will allow us to test if a specific integer exists within that list. So if we had the list containing the integers 1 through 5, in Python, a list is represented using square brackets like this, and we specify the contents using a comma delimited list. So here I've written 1, 2, 3, and so on. We'll actually introduce lists later on in this chapter, and then I'll give you much more detail on them in the chapter on data structures. But for this example, let's say we wanted to know if the integer 3 existed within this list. We can write 3 in and then give our list. And running the code block will give us back true since 3 does in fact exist within this list. Likewise, I can ask if 42 is not in the same list, which also returns true since the list doesn't contain the value 42. The other operator that I want to introduce is the is operator, which compares the identity of two objects, meaning it checks whether or not two objects are the same object in memory. In Python, it's possible for two or more objects to have the same value, but be different objects. So this operator allows us to check if, say, two variables are really referring to the same object or not. Objects, identity, interning, and related topics will actually be covered later on. So I'm not going to do an example just yet, but I did want to just define it here for you, since you're likely to have seen this operator in the precedence list. And I also want to point out in the subheading here, where it says is not, this is not a typo. The core developers of Python wanted to encourage readability as much as possible. And so this operator, when coupled with the not operator, is reordered so that it reads more like English. The comparison operators in Python are all given the same precedence, and the grammar supports chaining of these operators. So let's say we had some variables, a, b, and c. So I'll say a equals 5, b equals 9, and c equals -1. With chaining, we can actually write expressions like the following. A is less than b, which is less than c. And this works just as you'd expect. Or maybe to be more clear, This A is less than B is less than C is actually equivalent to A is less than B and B is less than C. So you can see how chaining these types of operators can make things a bit more readable and certainly easier to write. Now, before I move on to bitwise operators, there's one more topic that I'd like to discuss, and it has to do with truth value testing or boolean conversions. In Python, any object can be tested for truth, and the rules for this are discussed in more detail at the link here. Basically, what this means is that if you use an object in an expression that's expecting true or false value, Python has rules to evaluate or convert this object to true or false. For example, any non-zero integer is considered to be true, while the integer 0 is false. And this actually coincides with many other languages like C or C++. So we can write things like this, where I say not, and then maybe in parentheses I put 9 and 0. And we get true as a result because the 9 was converted to be true, and the 0 is converted to be false. Now note, we don't have to actually hard code the values in this way, the 9 and the 0, for instance. These can, of course, be the result of some computation or the output of a function or whatever. Python also supports a number of bitwise operators like and, or, exclusive or, left and right shifting, as well as complement. Unlike the previous operators, the bitwise operators do not treat the inputs, which are typically numeric, as single values, but instead treat them as strings of bits. That is, these operators, as the name suggests, operate on the actual bits that represent the values. For instance, we can create a variable num with the value 42, and we can see the binary representation of that number using the binary function, or bin. The output of this function is a string, beginning with the prefix 0b, indicating that the value that follows will be a binary representation. Those bits will be listed from left to right, with the highest order bits on the left and the lowest order bits on the right. So for our example 42, if we were to start from the right-hand side, we would have 0 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 squared, plus 1 times 2 cubed, plus 0 times 2 to the 4th, plus 1 times 2 to the 5th. And of course, we can see the expansion up here in the text as well. Now, in order to perform a bitwise AND between two integers, we could write 42 and 40, where we represent the AND with an ampersand. And this operation gives us back the value 40. Now, to see how that works, I've actually written out the bits for both 42 and 40 here in the text above. And so we can see that if we start from the right-hand side, we say 0 and 0 gives us, of course, 0. 1 and 0 gives us 0, and so forth. The resulting bit pattern at the end represents the value 40. So 42 and 40 is 40. And of course, we can use the bin function here to verify this. Similarly, we can perform the bitwise OR using a single vertical bar or pipe character. This enables bits in the output if at least one of the corresponding bits in one of the inputs is enabled. And if I use the bin function here again to output the result in binary, you'll see that this matches what I have here in the notes above. The exclusive OR operator is represented by the caret or circumflex character. This is similar to a bitwise OR, except that it only enables bits if the corresponding input bits are different. So if we reuse our example again, we see that the only bit differing between these two inputs is in the position representing 2. The left and right bitwise shifting operators are represented by two left or right angle bracket characters. These operators actually move all the bits of its operand to the left or the right by a specified number of bits. If we're shifting to the left, then this effectively pads the right-hand side with a specified number of zeros. If we shift to the right, this would effectively remove that number of bits from the right-hand side. As a side note, with respect to the integers in Python 3, Python will actually add any number of bits required to store a particular value up to memory limits. So Python will automatically adjust the number of bits it uses to store the result of an operation to prevent an overflow from occurring. So to see an example of a left shift, let us write 42 left shift by 3 bits. So again, this is going to move all the bits to the left 3 positions, meaning that each bit will move to a higher order position. So for integers, this is equivalent to multiplying the original value by 2 raised to some power, where the power is equal to the number of bits shifted. So if I multiply 42 by 2 raised to the third power, since we shifted by 3 bits, you'll see that we get the same result here. We can also see this if we output the binary representation of these values. Let's start with the binary representation of 42, and then output the shifted version of this as well. And you can see that we padded by adding 3 zeros here to the right-hand side. Now, if shifting to the left is equivalent to multiplying by some power of 2, then shifting to the right should be the same as dividing by a power of 2. But since we're talking about integers, in this case, it's really like using a floor division. So if we were to shift 42 5 bits to the right, you see that we get 1 as a result. And of course, we get the same output if we use Python 3's floor division operator. The complement operator is represented by a tilde and flips every bit from 0 to 1 and 1 to 0. This is known as 1's complement. Python actually stores its values using 2's complement, and so the complement operator is actually equivalent to -x minus 1, where x is the input to the complement operator. So we're not going to get into why Python, like many languages, uses 2's complement, but I've given you links here to the 2's complement page in Wikipedia, as well as the wiki.python page on this, which gives you much more information as well as some examples. Now, because the complement operator flips every bit, and because Python uses 2's complement, this has the effect of changing the sign of the value. So positive values become negative and negative values become positive. Unfortunately, this means we can't use the bin function as we have in previous examples to display the bits for this. The bin function simplifies the output for negative numbers to make them more readable. So for example, if I write bin 5, we get 101. And if I were to do the same thing for -5, we still get 101, except that the output now includes the negative sign here at the beginning. The bin function is effectively giving us the sign of the value followed by the binary pattern of the absolute value of the input. This is not actually how it's stored internally. So because of this, we're going to use a different function in order to display the bits, and I've written that function for you here. Now this function assumes a fixed width, or a fixed number of bits, and outputs the bits directly without the simplifications used by the bin function. You don't have to understand the internal workings of this function, but I have given you a link here to the format string syntax in case you're interested to see how this was done. So as a sort of sanity check, I can write bin 10 to output the binary representation of the value 10, and then we can use our new function to binary to output the same value using a fixed width. So you see the only difference between these is that this function outputs an additional 4 zeros on the left-hand side, whereas the old bin function truncated the same zeros. So now if we return to the complement operator, if I take the complement of 10, we get back -11, which is, as we said, -x minus 1, where x equals 10. Now if we're to write this in binary, so I write 2 binary with a complement of 10, we see in the output here that every bit has been flipped from our previous call to 2 binary. The first 4 bits went from being 0 in the first output to all being 1s, and the remaining 4 bits went from 1010 to 0101. And of course, if we convert -x minus 1, with x being 10 here, you see that we get the exact same result.